Okay, here is an old file, nearly a year old, that I realized I never commented on and never showed you. What I'm doing here is I'm running a digital signal from the audio precision to the DSS. Obviously, it only takes digital signals. And then the SPDIF receiver converts it into I2S and sends it to the DSP, as we know. The DSP processes it. And then instead of looking at the analog output of the speakers or even the line level DACs, I'm taking the I2S signal out from the DSP before it goes to the SAA7350 DACs, and we're converting it using a Wolfson 8804 chip back to an SPDIF signal and sending it back in the digital domain to the audio precision. So now we have isolated every analog component. We're essentially just looking at a digital in, digital out signal, which means that we're only looking at the DSP. And the point of the exercise is to try and see if we can reproduce the weird measurements we saw on the analog output. And we will no longer be able to blame clipping or noise or anything else, because essentially we're looking at numbers now. So some of the measurements that we're going to be looking at is the frequency response versus the volume, and also the frequency response versus the level. So let me explain the difference here. As a little resume, the Philips DSS930 applies the volume partly in the digital domain and partly in the analog domain by engaging transistors that gain down the signal, I think about 8 dB, and all the intermediate steps are done in the DSP. So the DSP is aware of the system volume, and it uses this in order to change the DSP processing when the level gets louder, and I'll show you that here. Here we're looking at the digital gain, and the input I applied was minus 20 dBFS, so we are far away from any 0 dBFS clipping. This is literally just to characterize the DSP. And what you see is that depending on the volume level, the bass boost has a different amount. So the idea behind this, if I understand the AES paper, is that the designers thought that as the volume increases, the output absolute level will obviously increase, and at some point the woofers will hit their maximum excursion. We'll see if we remove some of the lower volumes, is that as the level goes up, the amount of bass boost is going down until there is essentially no bass boost left. So this has nothing to do with our distortion problem. This is just characterizing what the DSP does and trying to see if the effect that was described in the AES paper is actually present. So this is actually a pretty clever idea. You get more bass boost for a given excursion, so this is all positive. But now we go on to frequency response versus level, and you can see that the level increases here all the time, and the gain should at this point be the same, because we're no longer changing the volume. So the DSP has nothing to change the characteristic for it. It's on a fixed volume level here. So all of these lines should essentially overlap. As the level increases on the input, the level increases on the output, and the calculated gain should be the same. And the level, of course, on the output you can see coming up here. Now, here on the level plot, it's clear to see that at some point we're reaching a maximum here, which is 0 dBFS. And there is not much digital space above 0 dBFS. In fact, there is none. So you clearly see it clipping here. And if you look at the gain, you see that because we're in a fairly low volume setting, we're still trying to apply that bass hump. So if I remove some of the lower levels, you will see that the higher we go, the more we sooner or later get completely stuck at 0 dBFS. So the picture is starting to look quite bad, and also some interesting things are going on. We see that here we're running up to 0 dBFS, and you know it's still trying something, but it's not looking good anymore. At the same time, what we're starting to see is that at the top end, it's also going wrong really badly, and that is something that is not so easily explained. So zooming in on one of the loudest curves is, we're looking here, right? We're seeing that it runs into 0 dBFS, and we have a big problem here because we saw the curves massively changing. But what you can also notice is, if you look at the tweeter signal, is that the tweeter signal is also completely distorted now, and even the woofer low pass filtering is completely distorted. And this is quite interesting what's going on here. So from about, let's say, minus 40 BFS, we now see a proper low pass filtering function again, and the tweeter signal is also okay. But when we go up to minus 3 dBFS, you see now suddenly that the woofer low pass is completely broken, and here the tweeter is impacted as well. So the problem is not just here hitting 0 dBFS, because if we did with a proper limiter, we could say, okay, well, it's not ideal. A sine wave will turn into a square wave and that's it. But something here is going entirely wrong, and it's impacting the tweeter signal. And this is very bad. Obviously the woofer is not meant to handle high frequency signals, so that will give you some distortion. But obviously the tweeter here is impacted, and this is its working area. So now, for some reason, because we are hitting 0 dBFS here, everything is breaking over here. And I'll show you this in the next picture, where we simply input a sine wave of 0 dB and look at the time domain. So now this whole expensive measurement machine is just turned into an oscilloscope. But look at this. This is supposed to be a sine wave. So if we're looking at the woofer here, I think it's a 50 Hz sine wave. This is not exactly round, but it still has the right periodicity. And here we see the absolute carnage that's going on. The signal is going over 1.0 fs, so over full scale. And after that, it's anybody's guess. You would literally have to know the architecture of the DSP and the source code, exactly how it's implemented, how it comes to fall down on 200 milli and then goes back up with a little peak. Then here it has the sort of shape of a sine wave. I think this part is supposed to be over here. Then it falls down again, it peaks again, and now suddenly it looks like a sine wave again. So there's some wrapping, some overflow, some underflow going on. Why suddenly it limits quite linearly, I don't know. You really have to look into the source code. But, you know, you could say that's a little bit of distortion and it's all fair enough, deal with it. But now look at the tweeter signal. It's a 50 Hz sine wave, so the tweeter is supposed to have a tiny, tiny, tiny little sine wave, suppressed by 60-70 dB. But whenever the woofer glitches out, you can see that the tweeter now has a full scale, almost 1.0 fs signal on it. And the only explanation here is that the tweeter signal is calculated as 1 minus the woofer signal. So the moment that the woofer signal comes down, the tweeter signal goes up. And these are pulses that are anything else but nice. But it does explain sort of the picture you saw here, that there are now very high frequency distortions in the woofer signal, even though it's trying to play something over here. It's actually trying to play 50 Hz here. But these quick pulses manifest in the frequency domain over here, and they also impact the tweeter signal. So this is just the worst thing you can have happen, actually. So now your tweeter signal has a double modulation of 50 Hz but full scale on it, and this is not something a tweeter is designed to handle. So these poor ribbon tweeters, and they cannot handle this, and they should not handle this. So if you still play with the original DSP, keep your input signal under minus 10 dBFS. And if you want to play full input range, I don't think there's any other thing we can do except redesign the DSP. And then the next question is, of course, are we going to try to recreate the original coefficients? Can we somehow get them out of the flash, or can we recreate them from the AES papers and the measurements in this file? Or do we just design a parametric EQ and redo the tuning from the beginning and go from there? That, I think, is something I'm gonna leave to the next installation. I don't know, the next year or so. See you later.